chemical equilibrium. So in chapter 15, the whole thing was this rate constant, right? Lowercase k. Now we're going to see capital K. And what capital K represents is something completely different. It represents the equilibrium state of the equilibrium constant. Really what it means is the equilibrium state of a reaction. Whether it's at equilibrium more towards the products or more towards the reactants, meaning which ones are in higher concentration, products or reactants. So we'll talk all about that today. So a couple of things formatting with this PowerPoint that, well, really one thing that sucks is for some reason the formatting, this kind of script F, view this as a double-sided equilibrium arrow, meaning that for the equilibrium equation. Wherever you see that in this PowerPoint, it will be a double arrow. I will try to change it everywhere it shows up, but it shows up a lot. So I couldn't change it manually because I don't know, it's just, these are made in, oh, it was made 2020. Well, whatever, whoever made them, I don't know. But just keep that in mind. I hope it's not too big of a deal, but that weird F is a double-sided arrow. And we use this double-sided arrow to denote our dynamic equilibrium, meaning the reaction can go forwards and backwards. It can go from reactants to products or from products to reactants, either way, until equilibrium is reached. So here's an example that we have in our body where we talk about hemoglobin. Now, hemoglobin, it is dependent on O2. So it carries oxygen. Hemoglobin is a big protein that carries oxygen to our tissues. Now, the relative amount of hemoglobin O2 and then hemoglobin O2 complex, if those concentrations vary until a point where they have equilibrium. So the reaction is right here. So it's hemoglobin plus the oxygen equals the oxidated or oxidized hemoglobin. And if this reaction has this, they all have an equilibrium constant K. Now, what we're going to learn is what K is. In the large one, indicates a high concentration of products. And we'll talk about that in what happens with in the body. So for O2, so you think about if you breathe in O2 and you have a high concentration of oxygen in your lungs, the equilibrium for this equation shifts to the right. Because what you're doing is, if you view an equilibrium equation, what we're going to do at the end, kind of view this as a scale or as a teeter-totter, not a scale. Well, scale too, but a teeter-totter, right? And you want to keep it balanced. That's what equilibrium is, when you have this teeter-totter balance. If you add O2, meaning increasing the concentration of O2 in your lungs, to the teeter-totter, what's going to happen? It's going to go to the left. In order to re-equilibrate or to get it back to equilibrium, what do you want to do? You want to push the teeter-totter or push the weight to the right. That's exactly what happens in a chemical reaction. To keep it at equilibrium, they're going to be, the reactants and products are going to be at different concentrations than they originally were because you have more stuff. But the equilibrium concentrations will stay relatively the same to each other, meaning the ratios will be the same. And that big K, equilibrium constant, is what we're talking about, that tells us what the ratio is. So if you add a reactant, it would shift to the right. If you add a product, it would shift to the left. This is what we call Lachatier's principle, and we'll talk about that more towards the end of class. And it's pretty easy. And same thing, the opposite happens if you remove stuff. So if you remove oxygen, it goes to the left to replenish it. If you remove the oxidated hemoglobin, it moves to the right to replace it. So that's basically the same thing. But in the muscles, if you look at the muscles, the muscles have low oxygen concentration. So that's basically from this equilibrium if you remove oxygen, because all of it is used up by aerobic respiration. So to replenish that oxygen in the muscles, the reaction will shift towards the left, meaning the products that are there the reverse reaction will take precedence, and the oxidated hemoglobin will then break down, release its oxygens into the muscles, which would then increase the amount of O2 until equilibrium is reached. So it's, again, a teeter-totter. Yes. So what equilibrium is when, let's look at the graph. Here we go. So what it is, and you've seen this graph before, is when you have reactants, which are these two, and you have products, the concentration constantly changes. right? At first, you're going to have no products, all reactants. Time goes on, they decrease, decrease, decrease with a reaction rate, right? Our rate constants, we know all about that, until a point. So before we were talking about the left side of this graph. That was chapter 15. Now we're talking about the right side of this graph, which is when they're at equilibrium, what's going on. So when they're at equilibrium, you see that the rate, meaning the slope of these graphs, are zero. There is no net rate between the product formation or reactant depletion, which also means the forward and reverse reactions are equal in rate. That's when we have equilibrium. Is there any questions on that concept? Or if you want me to reiterate it in a different way?
Can you reiterate it, please?
Yes, what was your question? The slope is the rate constant. Well, it depends. Well, the slope, it depends what order it is. Right, but yes, generally the slope is the rate constant. When the rate constant is zero, it's not a reaction. The rate constant is never zero for a reaction. But I see what you're saying, so yes, you're on the right track. Okay, and then for the question, the online question we had, so basically, we'll use these tables. So here you have a reaction, right? We've seen this one before. H2 plus I2 equals 2HI. At time zero, you have all reactants, and you see in the pool all reactants. So in terms of molecules, you have 8, 8, and 0. Then at time, let's say you let some time expire, you now have a couple of molecules of products. Now you have 6, 6, and 4. Let more time go by. It's halfway finished. You have 4, 4, and 8. So what happens when this reaction goes on, the forward reaction slows down. And the reverse reaction kind of starts to happen. But the forward reaction still takes precedence, still happens faster, meaning there is a net turnover of reactants to products until equilibrium is reached. Then when you get to equilibrium, the products and the reactant concentrations haven't changed. What that means is the net reaction direction, meaning left or right, is done. So we can say the forward and reverse reactions are proceeding at the same rate. Like if you have 2 people enter the room from one door and 2 people leave the room from another door, that's what's happening. The number of people in the room is still the same at all times. So that's basically what we're doing. Does that make sense?
Yeah, it's better now.
Okay, awesome, awesome. Yeah, and then what I was talking about before with the oxygen is, let's say you have that room and you add 2 people to the room, like from the top, right? They don't enter the room, you just add them in. In order to maintain the same amount of people or the same concentration, let's say you have people inside and outside. You have 2 people leave, 2 people come in, 2 people leave, 2 people come in. That's equilibrium. If you add 2 more people to the room, they have to leave in order to maintain that balance, that equilibrium concentration of people on the inside versus the outside. So that's what basically, and also if we pick out, or if we be morbid, whatever, we kill 2 of those people in the room, we need to replenish them. So 2 people from outside need to come in to maintain that equilibrium balance. So that's what we're doing here, but less morbid, we're dealing with reactions. Okay, so here we go again. So here's definition-wise. So the rate of at equilibrium, the rates, keyword, the rates of the forward and reverse reactions are equal. But the concentrations are not. It's very rare, I've never seen a reaction that the concentrations at equilibrium are the same. So just like we saw in this graph, the concentration change is 0, but the concentrations themselves can be very different. So keep that in mind. All right, so question. So which statement does not generally apply to a chemical reaction in dynamic equilibrium? And we call it dynamic equilibrium. What does dynamic mean? What do you guys think?
Is it always moving left and right?
Yeah. So dynamic means always changing, like it's always subject to change. It's like a dynamic motion. It's like, right. So this reaction is dynamically, it's always moving from left to right and right to left. But if it's in dynamic equilibrium, the rate of the left reaction is the same as the rate of the right reaction. So that's what we mean by dynamic. Nothing is static. So static equilibrium is another thing where you have no reaction at all, that's something different. So the answer where people put C, concentrations of reactants and products are equal. So we know that's not true.
Static equilibrium. Static equilibrium.
You know, the rates are equal. And the concentrations of the reactants and products are constant, which is true. They don't change, but doesn't mean they are not equal. Okay, so the law of mass action, that basically just means it's a definition meaning the products over reactants, but let's just skip to what the equilibrium constant, this infamous capital K, what it means. So here's capital K. It's the equilibrium constant. And it's different than the rate constant. Rate constant, lowercase k. Yeah, it sounds like a political term. A political term. I'm not gonna make fun of your spelling. I have terrible spelling. But yeah, so yeah, a law of mass action. Yeah, so that's what this equilibrium constant represents. Now, if you were to have this reaction, let's look at this reaction. We've seen this before, where we have A plus B yields C plus D, right, with coefficients. The equilibrium constant, meaning at equilibrium concentrations, the law of mass action applies, which means it's the products over the reactants. And it's very similar to the molecularity for rate law, meaning if we were determining the rate law for this, it would be rate equals lowercase k A to the A times B to the little b, like that. If we were doing the molecularity, that's how we'd represent it. But in this case, it's not just for reaction steps, it's for any reaction that has dynamic equilibrium. So, and also keep in mind, the biggest difference is like most of the reactions from chapter 15 only had one arrow, right? Meaning they went fully towards the products. For equilibrium, they all have the two arrows. If you don't see it with if it has one arrow, chapter 16 does not apply at all. So keep that in mind as well. So if you see, you might see different questions on the exam. Some of them have one arrow and you might throw you off. If you see one arrow that goes to the products, don't consider anything about equilibrium because it's just a forward reaction. Okay, so then to sum up this law of mass action, it's just simply the concentration of the products to their respective coefficient powers over the concentration of the reactants to their coefficient powers. So what this means, in other terms, it is a ratio between the products and the reactants. And we know that at equilibrium, the concentrations could vary a lot from reactant to product. So if we have a K value that is very low, what does that mean in terms of products or reactants? Which one is going to be more heavily weighted if we have a low K value? What do you guys think? Ding, ding, ding. We have two answers. And, oh, so three answers and one of them is right. So reactants. So reactants is right. So if K is low, to make this number low, that means we have to maximize the denominator, and that's the reactants. So if the reactants get larger in concentration at equilibrium, that means it is a low equilibrium constant. It's okay. So then if it's high, that means obviously the products will be higher in concentration at equilibrium. So let's do an example of solving for the constant. So anybody want to give me the answer for this one? So we're basically, according to the law of mass action, what is the correct expression for the equilibrium constant for this reaction? And ding, 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 D. D is the answer. So it would be products over reactants. So big K equals concentration of C cubed over A squared times concentration of B. And that's going to be option D. Any questions on that? No? Okay. Moving on. All right. So here's another one. So if you have this reaction, and remember again, the F means equilibrium. So you would do the same thing. It's the same thing every time that we have concentration of O, and then we have NO2 to the fourth over N2O5 squared. It'd be the same thing every time. All right, so now what it means, how to interpret K. There's two main ways we're going to interpret K. First one is by what number is it? And then we're going to compare it to another value. But what number is it? So if it's greater than 1, this means there are many more products of product molecules than reactant molecules. And that means that the position of equilibrium, so that's another term they use, is equilibrium position. That just means if you had a spectrum, meaning so 0, and then we're going to have all products, all reactants. If we had a spectrum of where the equilibrium lies for something that has a K value much larger than 1, that means the products over the reactants is going to be really large. The products are going to be heavier. This means that the equilibrium will probably be here. So if you had 100 molecules, we would say maybe 98 of them will be products when the reaction's finished, and 2 of them will be reactants when the reaction's finished. So that's what we mean by equilibrium constant. And vice versa, you can imagine if it's low, so low K, this means that the reactants are going to be more heavily favored. If that's the case, and you have 100 particles, reactants will have 98, and the products will only have 2. So the reaction will barely go forward at all, and it will just kind of stay at the reactants. And again, very rarely you have the concentrations as equal, and meaning a K of exactly 1. Any questions on that? No? Okay, so this is when K is less than 1. When it's very, very small, we have many more reactants than products. Yeah, so here's an example. You have a large equilibrium constant for this one, and in some you have a small equilibrium constant, meaning most of the molecules are still in the reactant form. Okay, so consider the reaction A to B. The images shown here illustrate equilibrium mixtures. A is the red and B is the black at 3 different temperatures. At which temperature is the equilibrium constant the largest? So think about that for a second. Then you can say or chat the answer. Oh, we have 3 already. 4, 3, C, C, C. Yep, the answer is C. Wow, you guys are faster. What happened to the speed when you're doing the worksheet? Oh, throwing shade. You didn't have pictures with counting dots on them. 1, 2. Rude. I'm sorry. I gotta throw shade every now and then. Keep you guys on your toes. And yeah, they were much harder than counting dots. So yeah, the reason why it's T3 is because this is more heavily weighted towards the black dots, which means product B. And then you have your equilibrium constant would be B over A. So the one that has the highest equilibrium constant will be the one with more B. Okay, so here's one that's a little bit harder. So the equilibrium constant for the reaction, again, A to B, is 10. The reaction mixture initially contains 1.1 molar of A and 0 molar of B. Which statement is true at equilibrium? So this is initial condition. When it's done, what do you think is going to happen? All right, so it's B, right? But the reason why is because initially you have all reactants, no products. So then we know our our equilibrium constant is 10, meaning heavily towards the products. So when the reaction is done, it better damn well be more towards the products. And in case B, that's the only place you have that. It must be 10 times more. So you have B is 10 times greater than A. So that works. That means B over A would be 10. So B is the correct answer. Okay. Oh, yes.
So because the equilibrium constant is 10, that means that there are more products than reactants, right?
Right. That means in this case, there happens to be 10 times more. But that's not always the case. It means there's definitely more. All the time there's definitely more. But let's say the reaction was 2B, right? And it was still 10. That means B squared over A has to equal 10. In that case, B is not 10 times A. But the ratio is still heavily towards the products. So the ratio of 10 is only the case because we don't have any coefficients here. Once we have coefficients and the exponents come into play, that changes everything a little bit. But the same principle applies where if you have K larger than 1, then you have a more towards the products, or an equilibrium more towards the products.
All right, that makes sense. Thank you.
All right, so the next thing we're going to talk about is how can you manipulate K? So remember we talked about, here's another reference to Hess's law in chapter 7, where you would flip equations and multiply them. So when you flip them, you would multiply the enthalpy of formation by -1, right? When you would divide them by a half, you would divide the enthalpy of formation by a half. This is saying, we're talking about what happens if we flip an equilibrium equation? What happens to our equilibrium constant? What happens if we add 2 of them together? What happens if we divide 2 of them? Let's find out. Or not divide 2 of them, but divide it by 2. Okay, so K forward. So K forward, that just means the equilibrium constant of this reaction going forward, just to reiterate, would be C to the C times D to the D over the reactants, which is A to the A times B to the B. If we were to write this equation backwards, it would just be flipped. And you could imagine that if we were to write the reaction backwards, which is shown right here on the right side, C plus D equals A plus B, same thing as the left one, but backwards, the equilibrium expression would be the same, meaning it would be the products, the new products, over the new reactants, which would just be the reciprocal of the other one. So K forward is the reciprocal of K backwards. Does that make sense? Or if not, any questions? Or yeah. Good question. No? Okay. All right, the next thing is if instead of flipping it, we multiply it by a number. So if you multiply an entire equilibrium expression by 2, you take, or sorry, if you multiply an entire equilibrium equation by 2, you multiply, or you take the constant to that power. So whereas for A plus B equals C, this is the original equilibrium constant. If we multiply everything by 2, meaning 2A plus 2B equals 2C, you now have the entire thing that it originally was, but everything's to the 2 power. So whatever you multiply it by, you take the constant, the terms of the constant to that power, or the whole, really the whole constant, because if you factor this out, it just becomes like that. Does that make sense? Good, okay. One last one. If you have 2 reactions, such as a reaction mechanism that you saw in the worksheet, but if these 2 reactions are in equilibrium, so let's say we have these 2. So A yields B and B yields C. to figure out the reaction for what A yields C is, meaning B is an intermediate. So let me just write this in these terms, B to C, like that. You can see how B is the intermediate, meaning it would cancel out on both sides. To write, and all we have is the equilibrium expression for each one. So B over A, and then K2 is C over B. All we do is multiply them together. So if we add equations, we multiply the equilibrium constants. And you can see how that works. It would just be C over A. And if you look, that's the same thing that happens if you cross out the intermediates and add the equations. If you add the equations, you get A yields C, then the constant would be C over A. And if you multiply the individual constants together, that's exactly what you get. Does that make sense? Are there any questions? Question? Nope, all good. All right, awesome, awesome, good, good, good. Okay, here's another one. It might be a little bit more complicated, but see, the reaction A to 2B has an equilibrium constant of 0.01. What is the equilibrium constant for the reaction B yields 1/2 A? So what do you guys think? Think about it, you're going from A to 2B. Now we're going from B to 1/2 A. The answer is not D. Sebastian's got it. It is B. But let's go over it, because that one's a little bit good. Good job in getting it so fast. You got to think about it a little bit. So let's look at it. Well, yeah, 1 over K, but let's just, well, not exactly. Well, 1 over K would be 100. So, all right, well, let's just go through it. All right, so you have the reaction, the first reaction. So it's going to be B squared over A. This is going to equal 0.010. What we're doing to this is we are flipping it. So if we flip it, we're going to take the reciprocal of it. So let's do that first. The reciprocal of it would be A. That's just flipping it, and it would be 1 over 0.01. Then, since it's divided by 2 or multiplied by 1/2, because the A is now 1/2 A and the 2B is now 1B, we take it to the 1/2 power because we're multiplying it by 1/2. So this would be the square root of this. So if we do the math here, the square root of 1 over the square root of 0.01, you get 1 over 0.1, which then equals 10. I'll give you a second. I got on a roll there. But if you want to do it, that was a tough way to explain. If you want to do it stepwise, well, that was it. I mean, if you flip it first. So if you flip it first, you have 2B yields A. So that new rate constant or equilibrium constant would be A over B squared. Then you're taking this equation, this is K, and then you're taking this equation and you're dividing it by 2. So B 1/2 A. So you're taking the rate constant and then you're taking the square root of it. Okay, so there's some comments. Why did B squared become B? It's because, good question, because when you divide the equation by 2, the b is no longer 2b, it's just b. So then the exponent for it is no longer 2, it's just 1. Or and this would be b to a to the 1 half, like that. You mean take the square root of it? Because, so let's go back. Go back to, so the question was, so if you guys can hear, the question was, she'd know why we take the square root of it. But that's a good question because I assume most of you have that question as well. So here, so when a coefficient of an equation are multiplied by a factor, the equilibrium constant is raised to that factor. If we multiply by 2, it's squared. In this case, we're multiplying it by 1/2. So it's going to be to the 1/2. The whole k is going to be to the 1/2, which is square root of. There, good. Okay, let's move on. All right, so we might not finish. Yeah, we're probably not going to finish. Whatever. We're ahead of the game. So if you have gases involved, so a gas, meaning it has pressure, not concentration, it's the same damn thing. Kind of like with rate constant you saw in the homework, where you can talk about concentration or you can talk about pressure. Same thing. You can take the partial pressures of the reactants, or sorry, the partial pressure of the products and put them over the reactants in the same exact manner. So that's a thing as well. So I'm not going to spend that much time on it, but what we do is we call it Kp. So we can take this just big K value, and technically it is what we call Kc. C stands for concentration, P stands for pressure. If you have a gaseous reaction, you could either have Kp or Kc. You can have both, because as we know, gases are the only thing that has a concentration and a pressure, because they're compressible, unlike solids and liquids. So there's actually a conversion to go from Kp to Kc, because not all the time are the pressures the same as the concentrations, or the ratio between the pressures the same as the concentrations. Most of the time they are, but there's some cases they're not. So does that make sense? Just those two expressions? It would be the same thing for gases as it is for concentrations. Yeah, okay. So now we can talk about them. We can talk about Kc versus Kp. Now in calculating Kp, the partial pressure is in ATM, right? So here's the equation. We'll cut to the chase. Here's the equation. Now what this means is that in a concentration-based equilibrium constant, we don't have to worry about pressure or the number of gas moles, number of molecules, because it's just concentration in a finite container. But when we have Kp involved, we have other things that are a factor on the equilibrium state. Those are temperature and also the number of particles, because that changes the pressure. So we can come up with this equation, which is Kp equals Kc times RT to the delta N. And again, this equation will be given on the exam. Now, what this means is that based on the temperature and the change in moles, so N is change in moles between the products and the reactants. So if you end up with, let's say you have H2 plus O2 yields H2O, this would be 2 and 2. If you have something like this, then it's always an absolute value. So then you would have the moles of the product would be 2, moles of the reactant would be 3. So the difference would be 1. It's always an absolute value. So delta, so it'd be 1. So then you would have Kc to get from the concentration equilibrium constant to the pressure, you would just multiply by that RT by RT to the 1. So that's how you figure out the difference in moles of reactants versus products. That will come into play again later when we talk about La Chatillier's principle. Okay, so here's another conceptual question. Under which circumstances are Kp and Kc equal for this reaction? So take a minute to think about it. It's a gaseous reaction, so think about it. Sumi, good job. Naomi, good. Naomi, that was kind of a questioning A, but you want to be confident when you type. So A is the correct answer. And the reason why is because there's no change in moles with A. Because if you have A plus B equals C plus D, that means the moles in the product and the reactant are the same. So delta N is 0, and then you have Kp equals Kc. So good job. All right. So also, you can have what we call heterogeneous equilibrium. And what that means is when you have an equation that has pure substances, such as a pure liquid or a pure solid, we don't include those in our equilibrium constant at all. Because what does an equilibrium constant need to have? It needs to have concentrations. So concentrations are only true for gaseous solutions or for aqueous solutions. We can't have concentration of pure liquid water. We can't have concentration of pure solid carbon. It's not in a solution, because we know a property of solutions is they have concentration, and they have a solvent and a solute. So even when we have a reaction that involves pure liquids or pure solids, such as this one, CO2 plus H2O, CO2 plus H2O yields H plus sodium carbonate. No, sorry, hydrogen carbonate. Then your pure liquid water will not appear at all in the equilibrium expression because it's not part of the solution. It's just a pure substance. So yeah, and here's another example when you have carbon. So you have solid carbon. It is not part of the equilibrium. It is not part of the concentration of the whole solution. And it has no effect on the equilibrium. All right, so here's more. So for which of the following reactions does Kc equals Kp? We want to think about it. When does Kc equal Kp? When the moles are equal. I'll give you that one. So when the moles of gases, of the products and the reactants are equal. So which one of these is that true? And yes, B is the answer. Good, because solids don't count, exactly. So for B, the equilibrium constant, so K, let's say we'll do Kc. So Kc is going to equal CO2 cubed, that doesn't count, solid doesn't count, over CO cubed. Since the change in moles, delta N is equal to 0, because it's 3 on the right, 3 on the left, then the Kc is equal to Kp. Okay, good. All right, so next we could talk about calculating equilibrium constants from concentrations, which it's plug and chug, basically. So what we can say is that if we do this reaction, so let's say we pick a temperature, because the equilibrium positioning does change with temperature. We'll learn that later. But if you change the temperature of a reaction, the equilibrium position will change. It might get larger towards the products or smaller towards the reactants. But what we can say is that at a specific temperature, let's say for this reaction, 445, if you have certain initial concentrations, and here we have 1, 2, 3, 4, 5 different trials of different reactant concentrations. What we have are end product concentrations. What will happen over time is that they will reach equilibrium. Their equilibrium concentrations are here. They're all different, right? Because you start out with a different amount every time. But the ratios of those amounts, no matter how much was added, is going to equal the same equilibrium constant once you plug them in. So this is a skill you should be able to do. They might give you tables on the homeworks where they're asking you to find the equilibrium constant for certain cases. And you can do that for that. So at every case, at a specific temperature and pressure, the equilibrium constant will stay the same. But the concentrations themselves will be different since you have a different starting amount. Good with that? Oh yeah, ice chart. Oh, Christina's ready for ice charts. Well, and Sumi, that's a really good question, actually. I'm gonna message my boss that after this or tomorrow. I'll ask her that. Good question. Yeah, I'll ask for those too, because this is the first time I'm teaching 126, so I don't have any, but I could definitely find those for you. They're probably gonna send them out to us in like a week or so, but I'll try to get them early, so that because we have more time, because we're smarter than everybody else. Well, I don't know about that, but we're more efficient. I didn't mean that as a diss to you. I meant as a diss to me. But you guys are smarter than everybody else. Oh, Sebastian, good question. So why 445? Just because that's what it said. So that was an experimental condition. If it was 450, they'd be a little different. If it was 100, they'd be different. Okay, ice tables. This is so much fun. An ice table. We might be done after. We'll finish after ice tables. So an ice table is a table that it's cold. It's really cold. No, but an ice table can help us calculate either an equilibrium constant, an equilibrium concentration, an initial concentration, whatever we're missing with a certain amount of information. That seems kind of vague, but because there could be a lot of different contexts of these ice tables. But we're going to do a couple after we talk about the reaction quotient. So if you keep this in mind, this concept is the main concept for chapter 16, is that when you have, oh, I should put my video on. So I have using my hands. So at equilibrium, you have specific ratio of concentrations that maintain the scale. I'll go this way, yeah. They maintain that scale, that teeter-totter. The reaction, and that's represented by the reaction, or by the equilibrium constant, that teeter-totter. Meaning the rates are the same, right? Going forward and backward, okay. The reaction quotient, all that means is, oh, you have the equilibrium constant, that's great. How about, what is that constant? What is that ratio? Not at equilibrium. At any point that's not at equilibrium, where is the teeter-totter? Is it here? Is it here? Is it here? Where is it? That is what the reaction quotient is. You calculate it exactly the same way as K, as Kp or Kc, but it is at a non-equilibrium condition. Or, I mean, it could be at an equilibrium condition. In that case, Q would equal K, which doesn't really have much meaning, but it's used to determine in which direction is the reaction going to go. So does that make sense? So it's basically K is for equilibrium only. So the concentrations of reactants and products over or at equilibrium. Q is anywhere else in the reaction time, not at equilibrium. You can calculate a Q. And if you compare Q and K, which one's bigger, which one's smaller, K stays the same, Q can change until it reaches K. That's what happens. So in every reaction, here, let's do an example. So let's say K is equal to 2. This means it's more heavily towards the products. The products have higher concentration at equilibrium. Okay, and all right. Then let's say Q, when you first start the reaction, is 0.1. This means a teeny bit of product was made, but it's mostly reactants because the reaction just started. If you have this information, which way is the reaction going to go? Towards the products or towards the reactants? What do you think? If at the specific instant, Q is 0.01. But we want to reach K. Because K is 2. So which way is it going to go? Oh, this might have stumped you guys. Not reactant. It's not going to go that way. So it'll go the other way. So, well, exactly. Yeah. So 50-50 shot. It's all right, Sebastian. All right. So thank you for answering. Thank you both of you for answering, because it's the fact that nobody answered means you guys are thinking about it a lot. And it's so, all right. Well, you got it right because there's only one wrong answer. All right. Think about it this way. I'm trying to think of an analogy. Oh, Christina, you're right. Good. So, so if you're, I guess we'll use people as an example. So if you have people waiting to get into a stadium, it doesn't apply now because of COVID, but if you have people waiting to get into a stadium, the reaction, meaning when they get into the stadium and the game begins, that is the reaction going at completion. Nobody leaves, or the people, let's say the people that leave their seat is the same rate, or no, it's getting too complicated. The people that leave the stadium is the same rate of the people coming in the stadium, like in like the first or second inning of a baseball game, whatever. Okay. Equilibrium is reached when everyone's in the damn stadium, all right? When they're all outside, there may be some grounds crew and like maybe 2 people, like not many people are in the stadium. So the reaction is barely started. So at that moment, Q is 0.01, heavily towards the reactants. This ratio is very low, very less than 1. As time expires and more people are let into the stadium, you can take a Q at any single point you want. What's going to happen to Q? If K is 2, meaning at the end of the day, you want to have all the people in the stadium more towards the products, Q is going to increase at every point in time until it reaches K. Exactly. It's a before, a during, and an after. Right. So Q is usually before equilibrium, or maybe even after equilibrium, after you add something else. But before it comes back to equilibrium, what is it going to do? Which way is it going to go? Does that make sense now? I'll do another example. So let's say we have K is, let's say Q equals 10, right? So now Q is really large. So at this specific time, it's COVID, and there are too many people in the stadium. So it's heavily, heavily towards the products, but the equilibrium is only 2. So it's still people in there, but just less people. So what's the reaction going to do? It's going to go back towards the left to want to regain and get back to that equilibrium ratio concentration, which is K. Okay, so are there any questions on that? No? All right, cool. Oh, another question. So Q's value is at a specific moment, the concentration ratio at a specific moment in time. You can compare it to K, but it's not, well, it can tell you how far it is from K, but it's not based on K. Right, exactly. Christina, you're on the ball. So Q is the same exact thing as K, but not at equilibrium. And it can tell you which way it's going to go to reach K. If it needs to go up to reach K, that means the forward reaction is going to happen. If it needs to go down to reach K, that means the reverse reaction is going to happen. So here's how that works. So if Q is greater than K, that means it's more at this point in time, at Q's point in time, it's heavily towards the products. Then what's going to happen is, since K is less than Q, it's going to want to go back towards the reactants. So the products will decrease, the reactants will increase. And then the reverse reaction will take place until K is reached. And then the opposite, yeah, so then the opposite, hold on, question. Yeah, so Q is only equal to K when it's at equilibrium. Correct, Luke. But we didn't get there yet. So again, Q is at a specific point in time, but it can dictate which way the reaction goes. So if Q is greater than K, the reaction will go to the left in order to decrease Q until it equals K. Once it equals K, equilibrium. And that's over time. When Q is less than K, it has to increase, meaning the forward reaction will happen, products will increase, reactants will decrease until equilibrium is reached, until Q is equal to K. And then again, when Q is equal to K, the reaction is at equilibrium. Yeah, so Q is at any point in time that's not equilibrium, not just equilibrium. K is only at equilibrium. Well, Christina, you should teach the class. That's good. I basically said the same thing, so you're just copying me. Okay. All right. This is a good slide. This is slide number 51. Summarizes the direction. So if Q is less than K, it needs to increase. So meaning the ratio needs to increase. Oh, wrong thing. The ratio needs to increase, meaning the products will be favored. Let's see. So the more Q is less than K, the more the products need to fill the gap, hence towards, yes, exactly, Sumi, good job. Q is greater than K, that means it's too much towards the products. The ratio at this point of Q is too much towards the products, then the reactants will increase, meaning it will go, the reverse reaction will take precedence, will happen faster. And then when Q is equal to K, that's when equilibrium is reached. Okay, this is a very good question relating the two. So let's take time to think about it. So for the reaction, N2O4 yields 2NO2. A reaction mixture at a certain temperature initially contains both of them at standard states, meaning 1 ATM each. So think about it. They're at 1 ATM each. Right away, before we read the rest of it, at 1 ATM, we can figure out its Q. We don't know if it's at equilibrium or not, but we can figure out its Q. I'm not going to do it for you. I'll let you guys figure it out, but we can do that. If Kp, meaning the pressures, so we're in terms of pressure, so that's good. If the pressure Kp for equilibrium is at equilibrium 0.15, which statement is true about which reaction mixture? Wait, which statement is true of the reaction mixture before any reaction occurs? So basically, which way will it happen? Say that again? Yes. Good, you got it. So which way will it go? Yeah, good. You memorized that, right? Good. Yep. Good. Okay. So Rebecca got the answer, but let's see what everybody else says. Yep, C to the left. Good. Okay, so what we can do is we can calculate Q. So Q is going to be, at this specific point, is NO2 squared over N2O4. And of course, these are pressures. So I didn't write here. I'll put P and P. Then this ratio will be 1 over 1, or 1 squared over 1, which is just 1. So Q is equal to 1. So another thing is, if it just gives you concentrations or gives you pressures, but it doesn't say it's an equilibrium, it's not an equilibrium. It has to say at equilibrium, the concentration is this. That's how you know it's an equilibrium. But for Kp, we know Q is 1, Kp is 0.15. So K is too big. So the reaction needs to go to the left to reverse that, to maintain the ratios. Okay, any questions on that? No? Okay, so last thing so here's what we're gonna do. We'll go through ice tables. We'll go through a couple ice tables, and then we'll probably be done. We'll do lecture at the air next week. You guys have been good. You guys have been great today, and I'll let you go out like maybe 2 minutes early after done with this. All right, so an ice table, what is it? You can find equilibrium concentrations using initial concentrations or pressures, or you can find K using this information. You can find a lot of things, but they all work exactly the same way. This is why practice is key. So we'll just do examples, and I'll show you how to set it up. So a reaction mixture initially contains 0.25 of CO, 0.4 of O2. At equilibrium, the concentration of CO2 is 0.15. Calculate Kc. All right. So what do we do? Very easy. Set up an ice table. I, C, E. What does I stand for? Initial, change, equilibrium. So what we do is we write down the concentrations initially. So initially we have 0.25 CO, all right? 0.25. Well, I'll write them in different colors. I'll use rainbow. Wait. Rainbow. 0.25. O2, we have 0.400. Now, what about CO2? It doesn't say anything, but what is it? No, so it's very easy. You're thinking it. No, easier than that. No, you're thinking too hard. Initially, you have that stuff, they're put into a beaker.
Is it 0?
Yes, it's 0. At time 0, you put the stuff in the beaker. What do you have? Right, exactly. At time 0, put the stuff in the beaker. What do you have? Just the stuff. Exactly. No products are made yet. That's initially. So time 0. Good. Now the change. Okay. Change. So the reactants with time, are they going to increase in concentration or decrease in concentration? Yes, the reactants are going to decrease because there's no products. So it has to go towards the right to a certain extent. We don't know this certain extent, which is why we're doing the ice table. So what we can do here is we can write, there's a lot of chats. Hold on. You cannot have negative products. Exactly, you can't. Yes, good. And then Ronit, negative X is correct. We'll get there. All right, so we'll just, So we will switch colors, red. So red will be the change. So the change is going to be how much it changes by, positive or negative. For 2CO's case, since the coefficient is 2, the amount it's going to decrease by is twice the amount of molecules than everything else with a coefficient of 1, because it has to be removed at a faster rate. So we'll do minus 2x. X is that value we don't know. We don't know how much it's going to change by. All we just know is that it's 2 times everything else because its coefficient is 2. Good, I love that. Oh, it makes sense moment. Awesome. All right, then O2, it's just a coefficient of 1. It's also a reactant. Therefore, minus X. Now CO2, like Christina said, it can't be negative, so it's not going to be minus. And we know the reactants are losing concentration. All of that, all those molecules are becoming products. Plus X, or plus 2X, sorry, plus 2X, because we have coefficient of 2 there as well. Good, exactly. Okay, so now we're basically done. All the rest of it is math. So what do? So it's math rather than chemistry. So rather than chemistry and math. So what do? Is we just add them up. Equilibrium, you're going to have 0.25 minus 2x. 0.400 minus x, and positive, oh, actually, wait, yeah, positive 2. We'll leave that for now, positive 2x. This is how you do it. Okay, so was there any questions on what I did right now? If some of you see what to do next, don't say it yet, but is there any questions on how I got to this point? No? All right, good, good. Awesome. So now, what other information does this problem tell you? At equilibrium, oh look, equilibrium, that's E. The concentration of CO2, oh look, CO2, we're getting somewhere, is 0.15. We didn't calculate that. We calculated it's 2x. Well, 2x is then equal to 0.15. Look at that. Boom, exactly. Good job, Ahmad. Then we can calculate x. X equals 0.075. And what are we being asked to do? Calculate Kc. And oh, we're really good at this. We know how to calculate Kc, right? So Kc, without any numbers in, is the concentration of CO2 at equilibrium squared over the concentration of CO at equilibrium squared times the concentration of O2 at equilibrium, not squared. This will then equal CO2. What's CO2? It's going to be 2 times X, which is going to be 2 times 0.075 squared over CO squared. Now CO, we just plug it in, right? We have 0.25 minus 2x, 2 times 0.075 squared times O2, which is 0.400 minus 0.075. So doing this in the calculator will get you Kc. Okay, ask questions. Good, total answer you got 6.92, sure. 6.92. If it's 6.92, that means this is pretty much, it's kind of heavily towards the products when it's at equilibrium. I mean, the concentration of the products will be a bit more. Good, good. Any questions on this? This was a relatively easier ICE table. Sometimes, and most of the time, the traditional problem is they give you Kc and they're asking you to find the equilibrium concentrations of everything else. In that case, you would have 2x squared over 0.25 minus 2x squared times 0.40 minus x equals whatever Kc is. Let's say it's 10. Then you'd have to solve for x, which you'd have to use the quadratic formula for. So this would probably be the hardest one. And so get your graphing calculators for that, but not right now. I mean, but I'm saying that's what you would see on the homework and a lot of the things like the traditional problems. All right, are there any questions on that?
So would we actually need a graphing calculator? Like for the exams, would they allow it or?
Well, so what you can do is, the best way to do things like this is to reduce it down to to a squared plus, or to not a squared plus b, to quadratic, to ax squared plus bx plus c, and then put it into quadratic formula.
But will they always keep the numbers that easy where we'll be able to?
Yes, yes.
Okay.
It's not going to be crazy. It won't be any crazy. This one I think is a little bit too crazy. Well, I mean, you could do it. This would be 4x squared on the top. This would be a little bit, this would be as advanced. This would be maybe too advanced, too much. Well, I got your back. Don't worry about it. Okay. All right, let's see what we got next. The what? Yeah. If you all got a 50, I know what happened. But I mean, last semester, everybody got 50s. Well, my class got 60s, but still, it's bad. The tests were hard last semester, I admit. Okay, so here's what we'll do. This is slide 56. We'll start there next class. We'll do one more example right now. You really have 5 minutes left. I hate keeping people longer, but we'll just do this one. So we have a bunch of stuff, and we have ice table. So you ever see an equation like that and you have a bunch of stuff, ice table. So we'll do this one kind of quickly. So I, C, E. All right, now let's read it. 2 molar of I2 and 2 molar of Br2 are initially present in a reaction mixture. That's it, initially. So we put 2.0, 2.0. How much of IBr? Good, 0. Because nothing happened yet. Calculate the equilibrium concentration of all of them at 425. Doesn't matter right now, but at 425, at some condition. Kc equals 100. All right. So I need your help for this one. What will be the change in I2?
Minus x.
Good, minus x. What about for Br2?
Same thing.
Good, minus x. What about for 2IBr?
Plus 2x.
Good, awesome, awesome, getting it. What about for equilibrium of I2? You can all shout it out if you know it. Good, 2 minus x. Br2. Good, 2 minus x. Well, it's inside voices. He's being considerate. All right, 2IBr. 2x. Good, all right, 2x. All right, so now equilibrium equation. Who wants to tell me the equilibrium expression? With or without the variables in it?
Would it be 2x squared over 2 minus x times 2 minus x?
Perfect. So the general term would be IBr squared over I2 times Br2, Br2, like that. Then this is going to equal 2x squared, meaning like make sure you don't forget parentheses, divided by 2x times 2x. Then this is going to equal 100. So this is the kind they'll give you. It's just a bit easier. So what you can do is you can combine things. So the top would be 4x squared. The bottom, 2 minus x squared. Well, or you could just do this. Hold on. This is a better way. Yeah, leave it to, yeah. It's so easy, I can't even do it. So you leave this squared. The whole thing is squared equals 100. Square root both sides. Yeah, exactly. So then you get 4x minus 2, like that, equals 10. Then you can cross multiply. Thank you. Then you multiply, cross multiply. So then you get, we'll move it over here, 4x, oh, 2x, whoopsie, 2x, I'm just testing you. I knew it was 2x. So you have 2x equals 10, or it would be, if we distribute that 10 into the 2 minus x, you get 20 minus 10x. Then you add, you get 12x equals 20. Then you divide by 12, and you get x is 1.67. I didn't do that in my head. I looked it up beforehand. So then there's other examples with that. We can approximate that if we have a large initial concentration and a small rate constant, or sorry, a small equilibrium constant, meaning the reaction is heavily favored towards the reactants, meaning it's a lot less than 1, we can say that the change, meaning x, so if we were to do an ice table, this 2 minus x, we can assume this x would be 0 in cases that have a very large initial concentration and a very small rate constant, which means the reaction will go towards the products in a negligible amount. So if in that amount is if the x value calculated is less than 5% of the initial concentration. So then we can say, oh, it's basically not going to change. So the last thing we're going to talk about is disturbing equilibrium. And this is what we call La Chatelier's principle. So it's saying that if we change either the temperature, the volume, the reactant or product concentration of an already in equilibrium reaction, what is going to happen to the reaction? And any of these disturbances and trying to restore equilibrium is what we call La Chatelier's principle. So it guides you on what's going to happen. And there's some things that we should think about is that it's not affected by the addition or subtraction of solids and liquids, meaning non-aqueous materials. Because as we talked about before, aqueous materials are the only thing that are going to be in solution and that we can calculate concentrations for. If you have solids or pure liquids, they are going to be present and may take part in reactions, but they're not going to be part of our equilibrium constants or reaction concentrations because they're not part of a solution. So the first thing we're going to talk about is adding reactant. If we add a reactant, and we'll just go very basic. So we'll just go brief. If we add a reactant, the reaction goes towards the right. Think of it as a balance. If you add too much to the left, in order to make that balance level off again, that reaction has to go to the right to balance it off. That's exactly what happens. So you add reactant, it proceeds to the right until equilibrium is restored. And keep in mind, the new equilibrium position is there. But the concentrations of reactants and products will be different because there's more stuff. But the value of the equilibrium constant will stay the same. In all of these changes, it does not change the equilibrium constant. Keep that in mind. Doesn't change equilibrium constant. It just changes the concentrations that are at equilibrium of the reactants or the products. So now if we remove a reactant, what's going to happen? The reaction proceeds to the left until equilibrium is restored. So same concept, meaning if you add too much to the right of the scale, to balance it off, has to go to the left. And then you can read all that. You can pause the video and read these points, which will be talked about in lecture. The effect of concentration changes on equilibrium. So it's just the basic, what we just talked about. Equilibrium shifts away from the side with the added chemicals or towards the side with the removed. So it's to restore an equilibrium. Getting back to baseline is what we're trying to do. And there's just a graphical idea. So then changing the volume. Now, changing the volume, would that apply for all types of reactions or just gases? And the answer is just gases, because for aqueous equilibrium, doesn't matter if it's in a small beaker, large beaker, you're adding solutions with concentrations. For gases, the pressure is a large component of how things react. Things can react at a higher pressure as opposed to a lower pressure. And the pressure dictates how much the molecules move. So it makes sense that if you change the volume of a gaseous reaction, it changes the pressure of the reactants and products, and in which the pressure equilibrium has to be restored. So first is we'll talk about reducing the volume. And think about it this way. Ideal gases have reactants and products. The moles of the reactants total, meaning the addition of the coefficients, might be larger or smaller. There might be a change in moles going from reactants to products. If there is, that means as the reaction proceeds, let's say towards the products, the pressure changes. It can go higher or it can go lower. So here's what we can say. If we reduce the volume, this means we're increasing the amount of space that the molecules can move, or sorry, decrease it, and we're increasing the pressure. If we increase the pressure, in order to relieve that pressure increase, the equilibrium will shift, or the reaction will shift towards the side of the reaction with fewer gas moles or fewer gas molecules. So in order to restore this kind of even pressure to where the partial pressures of the reactants and products will keep the equilibrium constant exactly the same, we'll keep it constant. So decreasing the volume causes the reaction to shift in the direction with the fewer gas moles. If we do the opposite, increase the volume, this is going to decrease the pressure. If we decrease the pressure, in order to increase the pressure enough to get to that same pressure that equilibrium was restored at, or to restore equilibrium, the reaction will shift in the direction that has the larger number of gas moles. So think about it as an ideal gas situation. Decreasing the volume makes everything have a higher pressure. We want to relieve that pressure. So the reaction is going to go where you have less gas moles. If we increase the pressure, where we increase the volume, we're going to decrease the pressure. To increase that pressure back to its equilibrium constant pressure, ratio of pressures, we want to move the reaction in the direction of the greater number of gas moles. And this doesn't change if you have inert gases or different types of non-solution entities in it. So let's talk about reactions now that are exo or endothermic. Now for exothermic reactions, or for either of these, for Le Chatelier's principle, where we're talking about the effect of temperature, we can consider endo and exothermic reactions as just like normal reactions, but you have heat as a reactant or product. So for something that's exothermic, meaning the heat is released, we can put heat on the right side of the equation. Now, if you want to increase temperature, that's like you're adding heat. So if you add heat, meaning this is just like the same as a normal product or reactant, if you add heat, the reaction will go towards the left, away from the heat, because this is an exothermic reaction. So we want to balance it out. And it'll go towards the reactant, and it would be a smaller K. For this case, if you have an exothermic reaction, if you remove heat, the reaction goes towards the heat to restore that kind of equilibrium. And adding heat will decrease the value of K. So K is based, so in this case, K changes because it's based on a certain temperature. So K is only true at a certain temperature, as we've seen from the rate constant. So rate constant changes with temperature. And so does the equilibrium constant based on, or rate constant because of Arrhenius equation. If we have an endothermic reaction, this means heat is on the left side. If heat's on the left side and we add heat, the reaction will go towards the right. So it's kind of like we're balancing out this teeter-totter, same exact approach. And adding heat to an endothermic reaction will increase the value of K because it goes more towards the products. And that would increase the ratio. So that's basically it. Here are some ice table practice problems you can do. You can pause and do some work on the screen, but we'll go over these in lecture.